Fine. Let's get on with today's session. Am I audible to everyone? Can anyone respond? Hello. Okay. Okay. Fine. I guess it's just the three of us. Let's get on with today's session. So, yeah, currently we are looking at mass transfer, and in mass transfer, so far we've looked at distillation, we have looked at adsorption, and we have even briefly looked at Fick's Fick's law. Okay. Today we'll be looking at something called drying. Okay. So yeah, let's get on with drying for today. So drying is the operation by which moisture is removed in relatively small quantities, and it is removed from solids, usually solids, or solid like materials. And the main process that happens here is evaporation. So before we move on, like, there is one important thing that we need to note. So there is actually a small difference between the process of drying and the process of evaporation. So drying and evaporation. So one of the biggest difference in drying versus evaporation. So the first difference is, in evaporation, the quantity of moisture being removed is in very large quantities. While in drying, the quantities are usually much lower compared to evaporation. And evaporation occurs at boiling point. So if you want to evaporate water from a mixture or something, the evaporation occurs only at the boiling point of water, which is at 100 degrees Celsius. But then drying can occur at even relatively lower temperatures. Okay. Yeah. So these are the main two difference I would say, when it comes to drying versus evaporation. So one other difference that we can say is, the vapor leaving an evaporator is generally pure water vapor. So like, this is in terms of the process of drying and evaporation. So in evaporation, whatever is leaving is only pure water vapor. But drying usually employs something like a carrier gas. Like it could be either hot air and something, or a flue gas or something like that. So that can also be present from the outlet of a drying process. So these are mainly the two difference, three difference between drying and evaporation. So the next thing that we want to see is some terms with related to drying. So moisture. So we have been looking at this moisture content. So moisture content is basically kilogram of water, which is usually said as kilogram of moisture per kilogram of dry solid. Then, when it comes to moisture, there are four different kinds of moisture. First one, we can call it as bound moisture. So, bound moisture, you know, sorry, one second. Yeah. So, bound moisture, you know, it is the amount of moisture in a solid. Okay, what happened? Oh, okay. Um, One second, guys. Okay. So, yeah, we we have four different kinds of moisture. So, first one is the. Okay, fine. Yeah. So we have bound moisture, which is basically the amount of moisture or water vapor in that sense, which exerts a vapor pressure less than the normal vapor pressure of water at any given temperature. So let's assume we have a solid like this, and let's say this is a wet solid, and it has a lot of crevices and cracks and all that stuff. Okay, so there are moisture which will be present on the surface of this solid, and then there will be moisture which are present inside the bulk of the solid. So usually these would be in these cracks or basically in the bulk of the solid. Okay. So this moisture which is present in the bulk of the solid can be vaguely termed as bound moisture. And this bound moisture exerts a vapor pressure less than the normal vapor pressure of water. Then this moisture which is not bound by any irregularities or like any um, surfaces, like for example the moisture that is present on the surface, we can call it as unbound moisture. So this unbound moisture will exert a vapor pressure greater than the normal vapor pressure of water. Okay. So basically it is easier to remove this unbound moisture compared to the bound moisture, because this unbound moisture will exert a higher vapor pressure and it will get evaporated much easily compared to a bound moisture. Now the next term is equilibrium moisture. Equilibrium moisture is the moisture content in the solid in a solid that can remain in equilibrium with the drying medium. Of a given relative humidity at any given temperature. Okay. And then there is a term called free moisture. This free moisture is the moisture in a wet solid which is in excess of the equilibrium moisture. It is important to note that only free moisture can be removed during a drying operations. This equilibrium moisture usually cannot be removed by drying. So in other terms, this equilibrium moisture, usually represented as X star, is the endpoint for a drying process. Now, let's look into the drying curve. So, a drying curve is basically a curve between the rate of drying with the moisture content of the wet solid. So, draw it like this. Okay. So, this is moisture and this is rate of drying. Okay. Now, let's say we are starting with a point A and the corresponding moisture content of this point A is Xi, which is the initial moisture content. So this drying curve initially will go like this. This is called the heating period. And let's say it reaches a point B, and from here the curve is flat. And let's say it reaches a point C. Then it will start sloping down. So it will, the slope is usually straight in the beginning, and then it will start curving a bit. And finally, it will reach a point where the rate is 0. Okay. Now, as I said, this Xi is the initial moisture content. The moisture content at this point C is called as critical moisture content. God. It's called the critical moisture content. Now, uh, Keshav, can you mute yourself? I can hear a lot of background noise. Okay, fine. All right. So, yeah, the moisture content at C is the critical point or the critical moisture, and this moisture, where the rate of drying is 0, is called as the equilibrium moisture, and that is represented as X star. Now, this flat rate regime is called as constant drying regime or constant drying rate. And this for this after this point C where the rate starts falling down, this regime is called as falling rate. Yeah. So the thing is, the moisture content at which the rate shifts from constant drying to falling drying rate is called as the critical moisture content, which is represented as Xc here. Okay. So we learned a lot of terms like the bound moisture, unbound moisture. Okay. Is it audible now? Am I audible now? Okay. Sorry about that. Yeah. Okay. All right. So, yeah. So we start from A, and A to B is called as the heating period, where we heat the solid to a given temperature. And after it reaches B, it will go to a flat rate, where the flat rate is called as the constant drying rate. And it will reach a point C, from where the rate will start falling down, and eventually it will reach 0. So the point at which the rate starts falling down is the critical moisture content, and the rate at which the drying rate is 0 is called as the equilibrium moisture content. So we have learned a lot of terms like bound moisture, unbound moisture, and so on. So generally, if we represent this, the constant rate regime usually takes care of the unbound moisture. So all the moisture content, like which are very easy to remove, is usually removed at this constant drying rate, and the drying rate happens very fast. And under falling rate regime, usually the bound moisture gets removed. Now, okay, to have a better clear idea, let's do one thing. Okay, all right. Now let's say the equilibrium moisture is somewhere like this. Okay, so this is the equilibrium moisture, and this falling rate, you can write it like this. All right. So let's say this is the equilibrium moisture. So this is equilibrium moisture. So then the free moisture is basically from here to here. So basically the sum of unbound moisture and a part of bound moisture is the free moisture. So in a drying process, we can only remove this free moisture. We cannot remove this equilibrium moisture. Okay. Yeah. So this is the basics of drying rate curve. And most of the questions in GATE from drying usually comes from a drying rate curve. Okay. Now, so there are like you can derive a lot of equations, and the main equations are basically the time required for drying. So let's look into that. So the time required. So let's say the time required for this constant drying rate, and let's say we represented it as Tc. This Tc will be equal to W by ANC into Xi minus XF. Okay, so let's say you want to dry a solid where the moisture content varies from these 2 points, let's say 1 and 2. So you can use this equation to find the time required for this drying process to happen. So here this W is the dry weight of the solid. A is the drying area and NC is the drying rate, which is constant. So this NC will be here. Okay, and if we write this drying time for the points 1 and 2, it will be like Tc is equal to W by ANC into x1 minus x2. Got it? Now, similarly, okay, we'll move to the next page. So, similarly, we can write the time required for falling rate, and that time will be represented as Tf, which will be equal to W by A, which is constant, and integral of xi to xf dx by n. So here also this n represents the drying rate, but the difference here is that unlike in a constant rate regime where the drying rate was constant, in a falling rate regime, this drying rate is a function of the moisture in general cases. So this is the equation for drying rate under the falling rate regime. So the total time required. Yeah. Uh, have any doubts, Riyas? Okay. Okay. So Xi represents the initial moisture content. And XF represents the final moisture content after drying. Okay. So let's say you have a wet solid which has somewhere around, initially it contains around 70% moisture. So this Xi will be 0.7. And you dry this, wet solid, and after drying you end up with, let's say, 40% moisture, then this xf will be zero point 0.4. So this drying happens between 0.7 to 0.4 moisture contents. Okay. Is it clear? Okay, fine. Also, one important thing to note that all this moisture content, all this moisture content are on dry basis. Okay, so do you know the difference between the dry basis and a wet basis? Okay, so dry basis. Okay, I'll start with wet basis. So wet basis, you represent kilogram of water by kilogram of wet solid. Okay, so this is basically kilogram of water by kilogram of dry solid, which is basically W in the formulas, plus initial moisture content which is represented in kilogram of water. So this initial moisture content is Xi in the formula. So Xi into the mass of water. So this will be M water. Okay, so this is a dry basis. I mean, sorry, a wet basis. So in a dry basis, yeah, so the dry basis is basically the moisture content without considering the initial water content. So this will be kg water by kg dry solid. Okay, so this is the main difference between dry basis and a wet basis. Is this clear? Do you need more explanations? Okay, fine. Let's move on then. So yeah, yeah. Can you explain? Hmm. Yeah, sure. Let's see. Mm, okay. So let's say, yeah. So let's say you have it is given that X, let's say X is the moisture content on wet basis. So let's say they have given that the initial wet basis moisture content is 60%. Okay. Now let's say you have 10 kg of wet solid. Okay. Can you guess how much in this 10 kg of wet solid with 60% wet basis moisture content will be the kilogram of water plus kilogram of dry solid? Like you have been given 60 percentage of this is water. So 100 minus 60 will be 40 percentage of this as dry solid. So now can you just say how much is the, just calculate 60 percentage of 10 kg is the water. So how much will it be? Okay. So it will be 6 kg of water plus 4 kg of dry solid. Okay. So together it will have 10 kg of wet solid. So this is an expression of the wet basis. Okay. And when it comes to dry basis, let's say the same 60% on dry basis for 10 kg. wet solid. Now we said that for dry basis it will be kg of water by kg of dry solid, and this will be 60% or zero point 0.6. Okay, so let's say here instead of 10 kg wet solid, it is 10 kg dry solid. Then this we have been given the initial moisture content as 60% for dry basis. Then this kilogram water by 10 kg will be zero point 0.6, and kilogram of water will be what, 6 kg. So then here what will be the weight of the wet solid? Wet solid will be dry solid, which is 10 kg, plus water, which is 6 kg, and this wet solid will be 16 kg. So now you can see like the difference here for the same moisture content expressed in different bases, one in a wet basis and the other in a dry basis. But then the numbers, for example, the weight of the wet solid and the dry solid, so these numbers are different. So this is the significance of wet basis and dry basis. So I hope it is much more clear or somewhat clear. Okay, fine. Let's move on. So here we looked at the time for the constant drying rate and falling drying rate. So the total time here will be Tc plus Tf, which is the sum of the drying rate for falling rate plus the sum time for the constant rate. So this T will be Tc plus Tf, and that will be W by A into Xi minus Xf. Let's say let's take it as here x1 and x2. Okay, we'll look into this in the during the problems. That's better. Okay, all right. So total time is the sum of constant drying rate time plus falling drying rate time. So yeah, these are the basics for drying, and let's look into some previous gate questions and problems, and maybe we'll get a more clear picture of how drying the process is and how questions come in drying part for gate. Okay, let's move on. Do you have any doubts? Yes. Okay, fine. Let's move on. Okay. Um, Hello everyone. Today, okay. So yeah, just read the question here. Sorry about that. Yeah. Okay. So is the screen visible? So just go through this question. A fiberboard sheet which is of the dimensions 1.5 meter into 2 meter into 15 mm is being dried by suspending it horizontally in a current of hot, dry air. The edges are insulated so that drying takes place only from the top and bottom surfaces. The wet sheet weighing 16 kg with initial moisture content of 60% loses moisture at a constant rate of 1.25 into 10 raised to minus 5 kilogram per meter square second until the moisture content falls to 30%. All the moisture contents are on dry basis. The time required for drying during constant rate period in hours is dash rounded off to third decimal place. Okay. Yeah. So in the question, they are drying a fiberboard sheet or basically something like a cardboard with the given dimensions 1.5 into 2 into 15 mm. And it is dried using a current of hot dry air by suspending it horizontally. Okay. They have also given that the edges of the fiber boards are insulated. So let's say no, this is a fiber board. These edges are insulated and the drying takes place only from this top part and this bottom part. Okay. And they have given that this wet sheet is 16 kilograms by weight, which has an initial moisture content of 60%, and after drying it comes to a final moisture content of 30%. Okay. They have also given that the drying rate is constant at 1.25 into 10 raised to minus 5 kilogram per meter square second. So they want us to find the time required for drying at this constant rate in hours. Okay. So let's see how to solve this. Okay. All right. So yeah, in these kind of drying questions, it is always better you represent it pictorially using a drying curve. So they have given that it is a constant drying rate. So in the drying curve, so we have the x-axis as moisture and y-axis as the rate, and this flat line represents the constant drying rate. Okay. So the initial moisture content they have given as xi as 0.6 and the final moisture content xf they have given it as 0.3. Okay. Now the rate is also given as 1.25 into 10 raised to minus 5 kilogram per meter square second. So now they have given us almost all the details that we need to find the time required for drying. So time required Tc will be W by A Nc into Xi minus Xf. Okay. So as they have mentioned, Xi and Xf are on dry basis. Okay. So that means they have given that initially this 0.6 60% moisture on the wet solid is in a dry basis. So we have to convert this dry basis or we have to use this dry basis moisture content to find the dry weight of the solid, which is represented by W. Okay. So given wet solid mass with 60% moisture on a dry basis is 16 kg. So we just saw how to find the weight using a dry basis. Now you can use this formula to convert wet basis into dry basis. Like It's you better make a note of this actually. So xi, the small xi is the moisture content on wet basis, and the capital Xi is the moisture content on dry basis. So Xi is equal to capital Xi by 1 plus capital Xi. So this is the conversion which you can use to convert, wet basis to dry basis and vice versa. Okay. So now we want to find the wet basis moisture content using this dry basis moisture content. So we have this formula. Now all we have to do is substitute the values for the xi in dry basis to find the values for the wet basis. Understood? Okay. So xi is equal to zero point 0.6 by 1.6, and that will be equal to 0.375. Okay. This is the moisture content on wet basis. We can use this moisture content on wet basis to find the mass of dry solid, which will be equal to mass of wet solid into 1 minus the initial moisture content. So this moisture content xi is a fraction which we just got it as 0.375. So whatever is remaining in the solid which is not moisture is the basically the dry solid part. So just substitute these values. So wet solid mass is 16 kilograms and moisture content is 0.375. We'll get the mass of dry solid as 10 kg. Then we just go back to our formula and substitute these values. So now we got W as 10 kg. Now we just need to find the area for drying. So as previously mentioned, the area for drying is the top and bottom part of the fiber sheet. So they have given the dimensions, the length as 1.5 and the breadth as 2. So the area for top side will be 1.5 into 2. Similarly, the area for the bottom side will also be 1.5 into 2. So 1.5 into 2 plus 1.5 into 2, that will give you 6 meter square as the drying area. So this is the drying area for top plus the bottom part of the sheet. So just substitute all these values for W and A and NC and XI and XF in the equation for time. We'll get TC is equal to 10 by 6 into 1.25 into 10 raised to minus 5 into zero point 0.6 minus 0.3. And we just do this calculation here. We'll get TC as 40,000 seconds. But we want this answer in hours. So we just divide this by 3,600. 40,000 by 3,600, which will give you the final answer as 11.111 hours. So basically what we did here is, this is pretty much a direct question. We have been initially given the values for NC. We just had to calculate the area A for drying, the mass of dry solid W by the mass of wet solid and the initial moisture content, and we just had to substitute these values in the time equation and we'll get the final answer as 11.111 hours. Is this clear? Let's move on to one more question. Okay. Now, this is a question from 2019 GATE, and it's basically a multiple choice theory question. So, in the drying of non-dissolving solids at constant drying conditions, the internal movement of moisture in the solid has a dominant effect on the drying rate during, and the four options given are the initial adjust period only, the constant rate period only, the falling rate period only, and D, both the initial and constant rate periods. Okay, so we'll learn something here in this question and while we are answering this. So again, we'll just go to the drying rate curve, and we have the x-axis and y-axis as moisture content in the x-axis and rate n in the y-axis. So we have a flat line which represents the constant drying rate, and the falling rate which ends at equilibrium moisture content x star. So we have this constant rate here, and we have the falling rate here. Okay. Now let's assume we have a wet solid. So like previously we saw the bound and unbound moisture. So let's take a wet solid, and we'll have a thin, very thin film of water which is present on the surface of this wet solid. Okay, and that wet thin film of water on the wet solid will get removed in the constant drying rate regime. So mostly a surface phenomena happens in the constant rate regime, or we term this as the unbound moisture. Now, when it comes to the falling rate, so once all this surface water gets evaporated, what happens is the moisture that is present inside this wet solid has to come out to the surface, and then only it has to get dried. Okay. So the moisture present in the bulk of the solid has to come out from the bulk of the solid to the surface of the solid. So it has to come out to the surface of the solid, and this coming out happens by two a few different forces basically, but two major ones are diffusion and capillary forces. Okay, so by these two actions, the moisture content present in the bulk of the solid will come out to the surface of the solid for drying, and this happens in the falling rate. So basically these mechanisms are generally termed as internal movement of moisture. Okay, so that means the surface movement of moisture occurs at the constant rate regime, and the internal movement of moisture occurs at the falling rate regime. So now we know the concept for this. We can just answer this question. So the answer will be the falling rate period only, which is option C here. So answer C, falling rate period only. Is it clear? Okay, fine. Okay, it's 7 o'clock. You wanna look into one more question, or you want to wrap it up for today? I'll leave the choice up to you. Okay, fine. We'll just look into one more question and then we'll wrap it up. So, yeah, let's move on. Okay, okay. So, in a batch drying experiment, a solid with critical moisture content of 0.2 kg water per kg dry solid. So, here you can see this moisture content is represented in dry basis with the unit kilogram of water per kilogram of dry solid, and it is dried from an initial moisture content of 0.35 kg water per kilogram of dry solid. So 0.2 is the critical moisture content, 0.35 is the initial moisture content to a final moisture content of zero point 0.1 in 5 hours. Okay. In the constant rate regime, the drying rate is 2 kg water per meter square hour. The entire falling rate regime is assumed to be uniformly linear. So that means the falling rate is basically a straight line. The equilibrium moisture content is assumed to be 0. X star is assumed to be 0. We need to find the mass of dry solid per unit area in kilogram per meter square rounded off to the nearest integer. Okay. So here in the last questions we only utilize the formula for the constant rate. Here we'll be using both the constant rate as well as the falling rate. So let's go to the rate curve. So we have the moisture and the drying rate in the x and y axes. So the constant rate as a flat line, and here the falling rate is basically a straight line. There is no curve involved in it. And the critical moisture Xc is given, initial moisture Xi is given, the final moisture Xf is also given. So Xi is 0.35, Xc is zero point 0.2, and Xf is 0.1. Okay. So let's, what else is given? The rate of constant drying. Okay. Yeah. Okay. Yeah. So we learned that the total drying rate, total drying time will be the sum of the drying time at constant rate and the time required for the falling rate. So this total drying time here is given as 5 hours. Okay. So this 5 will be equal to Tc plus Tf. Now, the formula for Tc is, we learned this formula just a few minutes ago. So this is the formula for time required for constant drying rate. And similarly, we learned the formula for the falling rate as well. So we can write that formula as well for the time for falling rate. Tf is equal to W by A integral Xe to Xf dx by n. So this is the general expression for time in the falling rate regime. Okay. So let's go to the constant rate regime individually. So we'll look at these things individually. So at constant rate, we have this formula here. So they have given that Nc is 2 kilogram per meter square hour. So Tc is basically minus W by A into Xc, which they have given us 0.2, and Xi as 0.35 by N, which is 2. Just multiply and divide these and we'll get Tc, the time at constant rate regime, in terms of W by A. So this W by A is the weight of the dry solid by drying area. So we need to find this W by A for the whole process. Okay. So now we just got this Tc in terms of W by A by just substituting the given values in the equation for time. We'll do the same thing again for falling rate. So for falling rate, time Tf is given as W by A integral of dx by n from xc to xf. So as I said before, yeah. So as I mentioned before, this n in the falling rate, this n is a function of x. So what is this n in terms of x is what we need to find out here. So if we go to the drying rate curve, this falling rate is basically a straight line starting from the points 0.2 and 2, and the bottom point represented as 0.1 and L. Okay. Okay. So basically this equation is in the form of y is equal to mx plus c because it is a straight line. Okay. So we can represent this sloping line as y equal to mx plus c. This c is basically 0 because we are assuming the equilibrium moisture content to be 0. So the c will go to 0, and we can write this y is basically n, which is the rate, and the small x is basically the moisture content x. And we can write the equation here as n is equal to 10x, or which is in the form of y is equal to mx, where m is equal to 10 is the slope of this line. And we can find the slope by mathematical methods. So the slope will be 10. So n is equal to 10x. Just have to substitute this in the equation. So Tf is W by A integral 0.2 to 0.1 dx by 10x, and just have to integrate this. Okay, integrate this from 0.2 to 0.1, and we can simplify this further as well. We'll get W by A 1 by 10 ln 1 by 2. We can rewrite this ln 1 by 2 as ln 1 minus ln 2. ln 1 is 0 and ln 2 is 0.693. So just write this here. We'll get the final answer for TF in terms of WA as TF is equal to W by A into 0.0693. Okay, so now what we basically did here is we just found out the time for constant rate and falling rate in terms of W by A. Okay, now what we have to do is we go to the total time required. The total time required is given as 5, which is Tc plus Tf. Just substitute the values for Tc and Tf here, and we'll get a linear equation with the only variable as W by A. And we need to find this only. We need to find the value for W by A. Right? So just substitute these substitute the values for Tc and Tf in terms of W by A, and just rearrange this equation. We can find the value for W by A as 5 divided by 0.075 plus 0.0693. and this will come, and if we do this division and everything, this value will come approximately as, let's see, 35 kilogram per meter square. So this is what we need to find in this question here. In kilogram per meter square, we need to find the mass of dry weight, mass of dry solid per area of dry. So just briefing again, what we basically have to do is we have to find TC and TF in terms of W by A, and we have been given all the tools and values necessary to do this. So we can find TC in terms of W by A and TF in terms of W by A, and then we just have to substitute this equation in the equation for total time. So the total time is equal to 5, which is equal to TC plus TF, and just substitute these values here, and the only variable remaining will be W by A, which is the mass of dry solid per unit area, and we can find the final answer as 35 kilogram per meter square. Is this method clear? Okay, it is yeah, like I feel like, if you keep working out these problems, these questions are basically, straightforward questions by just applying the time formula or the time equation for drying. So most of the numerical question from drying will be based on these formulas only. So I think if you just keep practicing these questions using this formula, it will be very easy to do in your gate exams as well. Fine, we'll stop here for today's class. Okay, slope. Okay. Uh, okay, we have. I'll show you how to find a slope once again. Let me just switch the screens. So I'll just give you the basic concept of how to find slopes for these equations for any straight line. I mean, so let's say you have a straight line like this. Okay, this is the x-axis and this is the y-axis. So any straight line can be represented by this equation y is equal to mx plus c. So this c here is basically the intercept of this line with the y-axis. Okay. So in the previous drawing question, this was 0 because this line was going to 0. So yeah. So basically y equal to mx plus c, and this c is the intercept. This m is the slope. Now let's take 2 points here. Point A, which is represented as x1, y1, and point B represented by x2 and y2. The equation for this y equal to mx plus c, this slope m is basically y2 minus y1 by x2 minus x1. Okay. So let's say in the question here we had point 2 and 2, and we had point 1 and what was the value? I think 1, I think. Okay. So the slope m is basically, you know, 2 minus 1 by zero point 0.2 minus zero point 0.1, because basically m is equal to y2. This y2 is basically, or y1, whichever like you are taking. So y2 we took it as 2, and y1 we took it as 1. This x2 is basically zero point 0.2 and x1 is zero point 0.1. Okay, so the slope m will be 2 minus 1 by zero point 0.2 minus zero point 0.1, which will be 1 by zero point 0.1, and that will be 10. Okay, so the last question, y equal to mx plus c, we said this c is 0. So this y is basically the rate n, and this x is basically the moisture content on dry basis x. So just substitute the value for slope here. N is equal to 10x. This is how we got the equation for slope, or the equation for the falling rate. Is this clear somewhat? Okay. Okay. So in the question, it is given that the rate gets halved. So initially the rate was 2, and the final rate gets halved, which will be 1. Okay. So yeah, right. So now it's clear, right? Okay. Fine. Let's stop here for today. So this whole month we've been looking at mass transfer. For a change, we'll switch subjects next class. So we'll start with CRE mostly. So have you learned CRE in your classes? Chemical reaction engineering, I mean. Okay, good. So we'll start with CRE. We'll actually try to go from the scratch, according to the textbooks and the syllabus. So we'll start from the rate equations, the order of the reaction, and we'll try to go in order for CRE. So I know, this mass transfer, we have been just looking at random, concepts from here and there. We'll try to go in an orderly fashion for CRE. So yeah, that's it for today, I guess. We'll stop here, and I'll see you next Monday. No. Yeah, thank you. See you on Monday.